All right, so in the last class, we basically the last thing that we discussed was how to handle K-maps with don't care condition. And the take-home message was, imagine you have a bunch of don't cares. You treat them as one if it helps you to get into bigger groups. And for example, for this case, if you treat this don't care condition as a one, it helps you to make bigger groups eventually. So we are treating it as one. And it is exactly the same as any other K-map. You could just convert this to a one if you want to, but I don't recommend that. But in your mind, it's essentially a one. So nothing else changes. The flexibility that you have is, you saw it in the next example. If you don't need it, if you don't need to cover it, you basically just ignore it and treat it like a zero, right? For this particular example, we had a few don't cares. We took one of them as one because that helped me come up with a bigger group, but the others were completely ignored, right? I didn't even try to cover this. And after that, it was all the same. And we have had, I hope, enough practice with making K-maps that you should be able to come up with the function for this one as well, right? If not, please let me know. And today we'll end this lecture with the 5-variable K-map, which is obviously a natural extension to 4 variables. So we are going to increase the number of variables eventually. And I hope you'll start appreciating why K-map has a limit. At some point, we'll have to move over to something else. So if you have 5 variables, when you had 4 variables, remember, we distributed 2 horizontally, 2 vertically, and we ended up with a really nice square-shaped grid. When you have 5 variables, you remember, every variable can have 0 or 1 as value, right? So imagine if you have A, B, C, D, E. A, B, C, D, E. You take one of them out, say A separately, and then you distribute B, C, and D horizontally and vertically, like we typically do. And you take 2 of these maps, 1, 2. One corresponding to A equals 0, the other one corresponding to A equals 1. Does that make sense, folks? Okay, so you take them separately, one corresponding to 0, one corresponding to 1 for one of the variables. You don't necessarily need to take out A. You could just take out, say, I don't know, A, B, C, D, E. You could take out E and then distribute A, B, and C, D. But I don't see any reason to do that, honestly, apart from confusing yourself, right? So to preempt the question, you can basically take out any variables if you want, but typically we always try to go with sequence. Take the first variable, use its 2 values separately, come up with 2 K-maps corresponding to the 4 other variables. Okay, now, how do you distribute numbers in a K-map, right? Let's do it. Let's do these example together. Are you with me? Remember, when you have 5 variables, can anybody tell me how many rows will you have in the truth table? How many? If you have 4 variables, how many rows do you have? When you have 4 variables, A, B, C, D, how many rows will you have in a truth table? 2 raised to 4, which is 16. I hope you remember that, right? Remember, like last one, we had 4 variables. How many cells did you have in the K-map? 16. Why? Because K-map is essentially another representation of the truth table. If you have 16 rows, you have 16, fields in the K-map, right? So similarly, when you have 32, which is like 2 raised to 5 is 32. So you have 32 rows in the truth table. So you need to have 32 spaces for possible values, right? So you see you have 16 here, 16 here. So 32 in total. All right. Now, let's move to this one. So in terms of min terms, your min term count will start from M0 like it typically does, and it will end with what? End with M31. Because there are 32 rows. If you start with M0, it will end at M31. Are you all good? Okay. It is just going to be a more rigorous, a process. You just have to spend more time thinking about it. But other than that, it's okay. Let me show you how to do it. Let me take one example here. Say 6, M6, the first one. Okay. What is, folks, in 5 bits, forget about the number of bits. What is the binary representation of 6? 1, 0, 1, 2, 3, 4, 5, 6. You see that? 1, 1, 0. So 1 1, sorry, let me erase this. 1 1 0 should be 6, but since you're dealing with 5 digits, I will add 2 more zeros in the front. So 0 0 1 1 0, that should be 5 in 5-bit number system, right? Do you all agree? So what is the location here? A should be 0. This is A. So I should stay here. Any problem so far? Okay. And then how about BC? 0 1. Where is 0 1? Right here. Where is DE? 1 0. Where is 1 0? Right here. So you should put a 1 in this location. Is it difficult? It's manageable, right? You can take any other random number, right? And for example, let me take M7. The next one. What is M7? Let me do it. 0 0 1 1 1. Okay, that's M7. Let's do it again. So again, A is 0. So we will be staying with this one. And then you have 0 1, which is BC. This is 0 1. And then you have 1 1 for DE. This is 1 1. So there you go. There is another 1 here. Okay. And for the case where you have a 1 in this location, you'll be getting to the other K-map and start distributing numbers there. So essentially, the process remains the same. You just have to deal with 2 different locations, 16 and 16. That's all. Are you all with me? Now, here is the tricky part. You have to pay attention to this. Remember, I told you that the K-maps wrap around, like horizontally and vertically, as if like this column and this column are neighbors. They don't look like it in a flat screen, but apparently it's a 3D structure if you think about it. It wraps around. And similarly, this row and the other row, they also wrap around. Now, imagine for a second, take this K-map and put it right on top of the other K-map, like a stack structure. Okay, then you see that every corresponding cell, like 0000 cell, which is this one, will be the neighbor for the other 0000 cell right here. Are you all with me, folks? Okay. I mean, we are not picking it up. There is a reason, there is a logic behind it. I'm helping you remember this by trying to help you visualize it. So apparently this could wrap around. For example, this is just a easier way to represent than that bit. There will be just one variable changing between these 2 columns. What do I mean by that? The fundamental principle of creating K-map was that between neighboring rows and columns, there will be just 1 bit difference. Did I tell you that? Okay, so between these 2 neighbors, notice there was just 1 bit difference, which is the first digit. Take 2 other rows, this one, between these 2 rows, there was just 1 bit difference. I mean, I use the term neighbor, so you have the physical sense of they being side by side. It makes it easier as human beings for us to, perceive this. But logically, it's not about neighborhood at all. It's all about just having 1 bit changing at a time. Okay. So similarly, if you haven't noticed, look at this column and the other column. Between these 2 columns, you just have 1 bit changing. Which one is that? Second one, the first one? The first one. See? So using the same argument, they should be like neighbors per se. That's what I told you. And to help you easily remember it, I told you it wraps around. That's all. Now, why am I telling you this again? Look at this cell for A equals 0 and this cell for A equals 1. You have 5 variables. Don't forget A, by the way, right? Simply because it is separated out. Between these 2 cells, do you think BC and DE change at all? They're exactly the same, right? 0 0 0 0. But what changes is the value of A. And you just have 1 variable changing, which is 0 and 1. The only difference between these 2 cells is in 1 digit, which is corresponding to A. So isn't that the exact same argument for any other neighbors? So to help you visualize it, I'm telling you, it's as if this map is on top of the other map. So now they're neighbor in a 3-dimensional space. But the logical approach is to just look for 1 bit difference. That's all. Are we all on the same page? Okay, now It's gonna be super easy to handle. Trust me. All right. Just pay attention for this once, and I hope it'll be done. Let's do it. So you have distributed all the ones together. Now we have to group them, of course. And that's where the tricky part comes in. Let's see. Notice what I'm trying to tell you is if you had just one K map like this one, you could have taken this as a group, this as a group, and done. You have covered all the ones. But now remember, this is part of the game. It's not a separate K map. It's part of the overall landscape per se. So notice this square and this square are basically as if they're right on top of each other. So it's a cube essentially, right? So if you think about it. So the way you group them is you don't just take them separately. You take these 8 ones as one group, not 4 and 4. 8 of them would be part of one group. And is 8 a valid grouping number, folks? 2 raised to 3. It's a power of 3. So yes, it is a valid grouping number. Okay, so I'm going to take 8. And using the exact same principle that we typically do for 4 input or 3 input K maps, we're going to come up with the expression for this one. Let's do it. Okay, let's do it here. Look at the variable that do not change. Do you think A changes between these two? Yes, A changes from 0 to 1. So A is out of the picture. Do you think D and E changes between these two? Notice. Okay, let's start with 1. Just look at D. Does D change between this and this point and this point? Just take a look at D. It's exactly the same everywhere. It didn't change. So we should take D. And it has 0 corresponding to the variable. So I should take D prime. Are you all on the same page? Okay, we have just covered this row. We haven't looked at the other one. Let's look at the other one, the vertical one. Take a look at B. Does B change between this 4, cases? No. So it doesn't change. And the digit corresponding to B is 1. So we don't need to prime it. We have B D prime. Okay. So you have basically covered 8 ones with just BD prime, which is right here. Any problem, folks? I told you the more you group, the easier the expression becomes. Okay. It looks like a very complicated, K map, but just look at the expression that we eventually can optimize down to. All right. Okay. Let's take a look at the next one. So this ones and this ones are right on top of each other. So you have 4, right? And let's do the same trick again. Do you think A changes between these two? A changes actually because you move over from A equals 0 to A equals 1. Does that make sense? That's the tricky part. I know. If it doesn't make sense, let me know. So when you move from this set of 1 to the other set of 1, between them, there is a difference in A. So you don't care about A. Take another variable, for example. Do you think D changes between these two? Actually, these 4 ones, right? There are 4 ones. D doesn't change. And what is the digit corresponding to D? 1. So I should keep D. Not prime, just D. Does E change between these two? Yeah, it already changed. So discard E. How about BC? BC, both of them remain unchanged, right? And what is the digit corresponding to B? 0. So I should do B prime. What is the digit corresponding to C? 1. So I should do C. So B prime CD. Right? Okay. Finally, there is one lone wolf, which is this one. Will I let this one be alone? No, I will just group it with something else. Does that make sense, folks? Typically, if possible, if I can bring the one with someone else, I'll always bring it into a group, even if that makes I'm repeating one of the ones. Like, for example, this one has already been covered, but just to help out the other one, I'll create a group between these two. I'm not making groups unnecessarily, just to make sure there is a group. Okay. Now, notice this is an interesting example. This is only limited to one of the K-maps, not the other one, which is fine. What it tells you is that you could just take ones in one of the layers. Left one or the right one, doesn't matter. Or you can take both, if possible. If they don't align, for example, if they don't align with anybody else, then you cannot take a 3D structure. You have to take 2D structures. All right. So for this particular case, let's see what do not change. Notice DE will not change because it's like literally in a column. So DE should be like D E prime because E has 0. What else doesn't change, folks? Does B change here? Does B change? Notice 0 and 0. So it doesn't change. So I should have B prime because the digit is 0. There is something else that doesn't change between these two ones. Can anybody tell me what that is? A, thank you. You haven't changed from one K-map to the other. So you're literally staying within A equals 1. So that is the other variable that doesn't change. So that's why you have A, B prime, D, E prime. Okay? So you have basically 3 product terms eventually. With this complicated function, you somehow manage to reduce it down to something really, really small. Yes. Great question. Yes, you're helping me project to the next one. Yes, and you gave me the answer as well. So the answer is, what if I have like 6 variables, A, B, C, D, E, F, right? What you do is you take 2 of them separately. Instead of 1, let me do it this way. A, B, C, D, E, F. You separate out 2 of them. And with 2 variables, what are the possible combinations? 0, 0, 0, 1, 1, 0, 1, 1. Does that make sense? So you have 4 of these K maps corresponding to 0, 0, 0, 1, 1, 0, 1, 0. At some point, it stops making sense, doesn't it? It is already a little bit difficult to kind of keep track of the ones and group them and not make a mistake and think about essential prime implicants, which I haven't even done here, right? You see my point here. And I told you the way this is structured is to show you at some point that, hey, this doesn't make sense. If it is something that you're thinking, you are in the right track. Yes. I mean, at some point it will stop making sense. Of course. Yes, it is definitely a game changer. K-map is definitely a game changer. We could still use it and we do still use it. But as you go to larger systems, it's basically loses its charm and utility. So there is a better solution which is beyond the scope of this course. This is typically a tabular approach, honestly, and it is more suitable for computer programming. So if you take courses like EDA, Electronic Design Automation, or Computer-Aided Design, like I said, I teach a course 651, for example, there you do everything with computers and you target problems that you cannot simply do manually anymore. So all of this that we have done is manual, as you see. You might be wondering, why don't we just go and learn that, the one that is being used? Because everything is built upon all of this, groundwork. If you don't understand this groundwork, you'll never understand the meaning of this. It's like, okay, just do this without any reason, any logic. That means at some point you'll be stuck with that forever. You'll never know the logic behind the progress, and you'll never be able to come up with the next set of innovation. At some point, 20 years down the line, 5 years down the line, things have to change. There will be new challenges. So if you don't go through the entire process of encountering challenges, coming up with a solution, and blah, 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 you'll not be able to handle the new challenges, right? That's the reason. So that ends this lecture. Any other question, folks, before I move over to the next one? The next one will be a bite-sized lecture. What I mean by that is it's a really tiny lecture, separated out simply because of the context, because it doesn't match with the next topic that we'll cover. So it doesn't make sense to merge them together and come up with a larger lecture. So it's going to be a very small one, and it will repeat many concepts. The 2 important new ideas that we'll cover in this lecture would be introduction of the 7-segment display and NAND-NAND logic. All right. And that's why the title says so. Are you all settled or am I rushing? Are you all good? Okay. Okay. 7-segment display. This is a classic example of when the students start learning digital logic. Even when I was an undergrad student, we always learned using 7-segment display. And you have all used it. If you have used a calculator, look at the digits. It has literally 7 segments in it, right? Like this one. And these are essentially LEDs, light emitting diodes. By activating a few of them, you could make one, or I don't know, like 7 or 8, blah, blah, blah. Like depending on how many of them are being activated, you can have different digits. You basically cover all the digits possible, right? 0 to 9. You cover 0 to 9 with just these 7 segments. Okay. So the logic behind it is basically how do you activate different, you know, LEDs. Now, we are first going to see how the logic behind 7-segment display work. And this is also a classic homework problem, sometimes lab problem. You'll also work on it, but you know, we are going to cover it in the class because it is easier for us to relate to real life that way. So notice, so you have 7 things to control. You have to control 7 possible things. How many combinations do you need? Can you tell me? To control this 7, you know, first of all, 7 segments. But how many digits do you need to cover? 0 to 9. How many combinations, basically? So 0 is 0, 0, 0, 0, for example. You don't know how many digits to use unless you see the last one. What is 7, folks? What is 7? 7 is 111. You know, 7 is 111. When you get to 8, can you stay with 3 bits anymore? No, you have to go 1 000. When you get to 9, you have to get to 1001. When you get to 10, it will be 1010. That's your, I mean, obviously, we don't have a digit 10. We stop at 9 in terms of digits. 10 is essentially repeat of the same digits. Okay. So we need to get to 1001 to accommodate 8 and 9. If it were up to 7, we would have done just fine with 3 inputs. But to cover the other 2, 8 and 9, we need 4 bits. You guys all agree with it? And there are a couple of concepts that we will cover with this simple idea. So we need 4 inputs because that will help us generate all the combinations. All combinations. You cannot generate, 10 combinations with 3 bits. You need 4 bits to, just for 2 of them. You could go up to 16, but decimal doesn't have up to 16, digits. We just have 9, 10, right? So basically we don't use the other options. And that's where the beauty is. Remember, don't care. This is a regular example of don't care combinations. Let me show you, first of all. So we have 4-bit WXYZ. When you have 0000, notice when you have 0, and there are 7 output. What do I mean by that? The output will control each one of these LEDs, and you will decide which one to turn on. Okay, let's try to make 0 first. How will the 0 look like, folks? And notice the LEDs have a name, and it is almost standardized. Most textbooks, most data sheets will use the exact same distribution. Okay, so it's kind of standardized. A, can you see this properly, folks? A, B, C, D, E, F, G. Like go clockwise and then somewhere in the middle. So to activate, to show 0, I need to activate all of them except G, right? So all of the output A, B, C, D, E, F should be 1 and G should be 0. Notice, this is my output list, A, B, C, D, E, F, G. All of them are 1 except G, which is 0. Does that make sense, folks? Okay, let's do 9. 9 is 1, 0, 0, 1, remember. To do 9, let's do 9 here. So I should activate everything except E. So where is 9? Right here. So everything has been activated except one of them, right? So basically, you see the point. So going from 0 to 9, you think about how it should look like here or somewhere else, and then you fill out the table accordingly, and you get your truth table. So this is gonna be a Boolean function with 7 outputs and 4 input. Do you guys all agree with it? It's okay. You just treat every output separately. Something that you guys didn't ask me was, what if I have a function? When you go to KMap, notice we always come up with one function. f equals something, one function. What if I have multiple output? How can you handle the k-map? That means basically you have to have k-maps for every output. K-map for A, k-map for B, k-map for, you have to treat them as separate truth table. So I'm asking the question, I'm answering. There is another classic example, which I hope you have worked on for lab 1. Sum, adder circuit. Remember sum and carry. There are two outputs. For sum, you need to have a k-map. For carry, you need to have another k-map. You treat them as like independent Boolean functions. That's all. ABC, sum. ABC, carry out. Done. Okay? Are you all good? Okay, now we are going to do a real k-map mapping one more time. So now we're going to, so all right, let me, before moving on, let's do it together. Can we do it together, folks? All right. So I want to maybe do a k-map for the output A. What I didn't mention is what happens to the other combinations. You have 4 bits. That means there are 16 combinations. You already need 10 of them. How about the other 6? What do you do with them? Don't care, right? So that's why I notice after 1001, the other combinations are, others are don't care. None of the output. We don't care about all the other outputs. And we'll see how that translates to the logic, Boolean logic. All right, let's do it. Are you guys ready? Okay. So I don't know if I have already done it anywhere, but if not, let's, let me show you a few examples. So for example, 0, 0, 0, 0 corresponding to A. So let's do it. 0, 0, 0, 0 should be 1. With me? All right. So what is the next one? This is the next one. 0, 0, 1, 0. So this is WX 0, 0, 1, 0. That means right here. Where is the other one? Right here. You know what? I just noticed there are many ones, but less zeros. So should we do the other thing? Should we do the zeros first? Let's do it. 0, 0, 0, 1. So 0, 0, 0, 1, it should be 0. What is the other 0? Right here. 0, 1, 0, 0. This is 0, 1, this is 0, 0. This is the other 0. Any problem so far, folks? Okay. All right. Although, do you notice that there is one challenge here? Did anybody notice that there is a challenge? What is the challenge, folks? The trick that I told you that you could use a shortcut, like, yeah, okay, instead of ones, just go and do the zeros. It doesn't fully work here. What is the reason? There are don't cares. Exactly. And there are many of them, 6 don't cares and 2 zeros, like 8 of them essentially. So if I were going for ones, I would have filled out 1 anyways. And if I were going for don't cares, but anyways, I need to do like, this is something, this is a case where you cannot really take too much of a shortcut. You have to do it properly. Okay. Because you don't know where the don't cares are. You don't know where the zeros are. You don't say after you fill all the ones, you cannot just assume everything else is 0 because they can be don't care. Are you with me, folks? Okay, so after covering the zeros, I've covered the zeros now. Now I'm going to cover the ones so that I don't have to cover the don't cares. So ones, this is the first one, 0, 0, 0, 0. Let me do it this way, 1. What is the other one? 0, 0, 1, 0, 0, 0, 1, 0. This is the other one. What is the next one? 0, 0, 1, 1. This is 0, 0, 1, 1. This is the other one. 0, 1, 0, 1. 0, 1, 0, 1. This is the other one. 0, 1, 1, 0. 0, 1, 1, 0. This is the other one. Hey, am I making sense to you all? Okay, don't feel left out. 0, 1, 1, 1. 0, 1, 1, 1. Right here. And 1, 0, 0. Like 1, 0, 0, 0. So this is 1, 0, 0, 0 right here. Finally 1, 0, 0, 1. 1, 0, 0, 1 right here. Okay, and the rest of them will be don't care. So don't care, don't care. All right. And now that you have it, I mean, obviously I'm not gonna give you an answer, for example, but we could do it quite easily if you want, if you think about it. Say you can easily take this 8 as 1 because don't cares could be treated as 1. You could take, this other 4 as 1 if you want to. And then, you could cover this ones together and these ones together, blah, blah, blah. So there are ways you can cover this. So everything else remains exactly how we practiced. But the uniqueness here is you are mapping a real system into a K-map. And where is the other trick? You have just covered A. So for all 7 of these outputs, you need 7 K-maps. So all 7 of them will have separate functional output. Are we all on the same page, folks? You look sad. Don't hesitate. Ask me questions. Okay. You look like me exactly when I was an undergrad. I was always like, okay, what is going on there? Anyway, so people learn in different ways. But for some reason, whenever I used to come to the class, that was the perfect time for me to sleep. Or like I used to feel sleepy. The moment I enter class, I was fresh. The moment I get into the class, like, one day, like I remember at the time I was at Penn State. Uh, I was sitting in the front desk, not because I wanted to, because I came to the class later. Like, everybody tries to get the back seats first. And then front rows are open for you to take if you come a little bit later. I mean, I wasn't late compared to my other friends. They came much before me, like 20 minutes before the class. So I was there and I was like, I dozed off. And after a while, the professor, he used to like make noise, ha, like during course, ha. And then I woke up, what happened? And he said, welcome back. And that was very embarrassing. It's like really embarrassing. I was like, I need 2 coffees before getting to class next time. Anyways, so if you're feeling like dozing off, I hear you, I feel you. That's why we have these recordings, I mean, even if you give up this moment, don't give up completely. Go home, listen to it later on in a cozy environment and come talk to me. Make sure you ask questions. Don't leave anything unanswered and like, okay, there is a gray area. I don't really know. These are found, like I said, this is a big responsibility that I treat it to be a big responsibility to help you create a foundation that will encourage you to pursue it further. Honestly, this is not the most cutting edge thing, as you can imagine, right? You are literally learning the foundation. But if this is shaky, no matter how far you go, everything else will basically fall apart at some point. So make sure you understand things properly. All right. So move to the next one. This is a very quick reference to the Basis 3 board that you'll be using for your labs. Simple FPGA board. I don't want to talk too much about it because we have labs and we have detailed instructions about it. Very quickly, you have like 4 7-segment displays. And this is a very simple example of how circuits work. Excuse me. You just have seen, excuse me, that there are 7 controllers, for example, A, B, C, D, E, F, G, right? For these 7 segments. So that's your 7 controllers. If you count them, 1, 2, 3, 4, 5, 6, 7 controllers. What is the other one? This just controls the dot. If there is a dot right here, I don't know if you notice that. It just controls the dot. Just one more thing. That's all right? And why do you have these 4 bits? These essentially select which display you want to use. So imagine you select this to be 1 and others are 0. That means this transistor turns on and activates this one, and the others are off. Okay, that's how you select. This is essentially your enable signal. There is not too much to discuss about it. We have covered the logical part of this display already, and hopefully you'll have some practice later on. So I'm excited to move forward with the core part and the most important part of today's lecture. And I think you should definitely pay attention to this. I already told you this initially in one of the lectures, but I'm sure it didn't really make that much impact and didn't make much sense. That's why you need connection. But I told you that there are some logic gates that are universal that can cover any Boolean function, like AND or invert. This is a combination. This is a set. AND or NOT gate or inverter, whatever. Some people call it inverter. Some people call it NOT gate. Doesn't matter. All it does is it takes zeros and make it 1, or 1 or make it 0. Just inverts the bit. That's all. It doesn't do anything else. It takes 1 bit. This is an 1 input Boolean logic gate. Just takes 1 bit, inverts it, done. Okay. So AND or and NOT. that is a complete set. It can implement any Boolean function in the world. There are a couple of other examples in the slide. Go and check it out. One example that should stand out is that a NAND gate is a universal gate. It doesn't need anybody else. Just by itself, a NAND gate can implement any Boolean function. This is a very powerful statement. If you think about it, all you have to do is make a NAND gate. And just to give you an example, you are dealing with super semiconductors now, these and that. For my research, this is a tangent, but like 30-second tangent. We are looking for completely new paradigms of logic design. We're going beyond transistor based. You haven't seen the circuits behind it. You're looking at the symbols. None of these are circuit, honestly. Although we ask, draw the circuit. You connect an AND gate with an OR gate, blah, blah, blah. You come up with it. It's not really a circuit. It is basically like a block diagram, honestly. So you have to get inside these blocks and see how the circuit really looks like. They're not complicated, but there are more to it, right? So all these circuits are, today's circuits are designed with MOSFET, right? At some point, it used to be designed with BJT. At some point, something else, right? So there are devices that change and the circuit design changes, but the gates and all the logic remains the same for decades. Nothing changed. Only the underlying circuits changed. Now, what I'm trying to do is do it with, say, superconductors or topological insulators. There's going to be like 15, 20 years down the line. Engineer, hopefully, computing system 10 years down the line or 15 years down the line, right? So superconductors, for example, when you come up with superconductors, and I have to show that it can be shaped into a generalizable Boolean logic paradigm. And imagine what I need to show. If I could somehow demonstrate that you could make a NAND gate work, I don't have to make a processor, do I, folks? If I could somehow show that here is a NAND gate, see, it works. The experts in the domain will not ask me questions about, why didn't you show me AND gate? Why don't you show? Because NAND is a universal gate. That means you could essentially implement a processor. Are we all on the same page? That's why I took the tangent. I mean, that's how powerful it is. When people look for new paradigms of logic design, new hardware platforms, new technologies, they just shoot for designing NAND or NOR or something like that. Yes, you could also design AND or invert, three things. It is much easier to design one versus three. All right. I hope I bored you too much. All right, so let's do it this way. Folks, this is a visual representation of a law that we have all seen, De Morgan's law. I don't know if you paid attention to this, but I told you, didn't I, that it has a lot of implication in logic design moving forward. It looks like a very simple mathematical law. If you have A prime plus B prime, plus doesn't mean add, it means or, right? Boolean algebra here. It will be equivalent to, can anybody remember, can anybody tell me what this is gonna be? A prime plus B prime. Anybody remembers? AB. So basically, if you take the OR of two inverted inputs, it is as if you could take the invert of the end of them. That's exactly what it means. But in terms of visual sense, notice you have A here and you have taken an inverter, you have inverted it to A prime. You have taken B here, you have inverted out to B prime. I'm not going to tell you why I'm doing it, but we'll see that later. But I'm just doing it for the sake of doing it, all right? I'm taking an inverter and just inverting these inputs. And the output that you're getting, this is an OR gate, right? You guys all agree that this is an OR gate? So this OR gate will give you A prime plus B prime. Is there any confusion with it? Should be fairly straightforward. So you are somehow creating A prime and B prime. You are taking an OR gate, so it should give you A prime plus B prime, which is the left-hand side of the De Morgan's law. What De Morgan's law tells you that doing this is essentially the same as taking a, folks, AB is what? AND or OR. When you do AB, is that AND or OR? AND. When you do AB, it's essentially AND. And then you take an invert. Invert means not, right? So AB prime is what? So AB is AND. When you take a prime, it does not AND, which is NAND. Right? So essentially, what I can tell you is this entire thing could be represented with a NAND gate. So this is the symbol of a NAND gate. Notice AND is like this. If you add a circle or a bubble in front of it, that represents NAND. So it's exactly the invert of AND. So can I say that I could replace all of this with just this simple block? And you can then deal with input A and B. If you do A and B, AND gate will give you AB, but NAND gate will give you AB prime. Are you all on the same page? If I could finish this slide, you'll be in good shape. Let's see. We just have half of this slide left. Let's see. So now, how many of you remember this format? This is a universal logic format for sum of product. Remember? So let me do it. Let me see if I have any. Yeah, A, B, C, D, E, F, G, H. Say you have a function. When I try to implement this A, B, C, what do? I take a AND gate, and then D, E, F, D, E, F, and then G, H. Right? Product term, and then how do you do the sum term? Take a OR gate, and you just sum them up. That's your function. Isn't that how we do things? And after you simplify everything, it all comes down to this format. Sum of product, typically. We don't typically do product of sum. If you absolutely have to, you can, but sum of product. That means when you do sum of product, your circuits will always look like a layer of AND gates followed by just one OR gate. Does that make sense to you? Okay. Series of AND gates, a layer of AND gates followed by an OR gate. That's how things look like. Okay, that's what you're looking at right here. Instead of 2, I could have done like 5, 7, doesn't matter how many AND gates. But all the AND tree will be feeding into the OR gate eventually. Okay, now I am going to change things a little bit. Please pay attention, all right? Do it. This is AND. Can I convert this to NAND and then add an inverter? So when you make it NAND, it will invert the output, and then inverter will take it back to whatever it was before. So isn't that the same as, so when I take a NAND gate and invert it, don't you get an AND gate? Are we all on the same page? Okay, so I'm gonna convert it this way. So convert AND to NAND and invert, NAND and invert. But hold on a second. Notice something? What is this segment? Did you just see that when the inputs are inverted and you're taking an OR gate of the inverted inputs, is as if you could replace this entire thing with a NAND gate. So can I replace this block with a NAND gate instead? So these guys become NAND gate. The other ones, the following stage also becomes NAND gate. So it's all NAND. Instead of having 2 types of logic gates, you can have just one logic gate, universal logic design. And I told you the power of this. Since you can represent any Boolean function using this approach that I showed you, any Boolean logic function, that means any Boolean logic function could be represented with NAND-NAND fashion. Is that logical? Any counter argument? Any confusion? Okay, so that is the big picture. That is called NAND-NAND logic. When you implement everything with NAND-NAND logic, we'll have one practice in the next slide. Let me show you. So this is, I mean, I don't want to go through the process. I'm going to show you what we are going to do. We are going to come up. This is essentially the last slide, as you see, right? I have 2 minutes. I don't want to rush it. I'll give it a shot. If you don't understand, I'll repeat it anyways in the next class, right? Let's give it a shot together. Okay, so this is the same truth table that we saw for 7-segment display. I just wanted to reuse it because I hope you can practice the K-map at home and come up with this function. This is going to be your functional output for the K-map. Okay, so for A, if you do it for D, it will be separate. If you do it for F, it will be separate, right? So let's do it for A. This is your Boolean logic function. Now, when I try to incorporate it in actual, circuit or, using AND and OR gate, here is how it looks like. W, this is your W. Y, this is your Y. X, Z. X, Z, this is an AND gate, and it is being fed into OR gate. X prime, Z prime. This is your X prime, Z prime, and it is being fed into the OR gate. Any new challenges here? Isn't that the same thing that we have been seeing? All right. So what you are going to do is then convert all the inputs with, say, for example, W, use two inverters. Two inverters. Using two inverters means it doesn't change. You change it and change it back. And you'll see why we're using inverter, by the way. Okay. So why? Use two inverters. X, Z, change this AND gate into a NAND gate and inverter. Does that make sense? The thing that I just did. Change the other AND gate into a NAND gate and an inverter. So what is the big deal then? The big deal is you can then change all this section because all the inputs are inverted and you have an OR gate into a NAND gate. See, so you have a NAND gate, NAND gate, NAND gate. It's a NAND logic. So don't worry, we're out of time. I'll repeat this in the next class and then we'll move over to new lecture. Thank you.